Okay, so hello and welcome back. So in the previous, not in the previous video, but the video before that, we did this experiment, and basically what now we need to basically go over the data that we have and see what we need to do with this 100 Hertz all the way up to 1 kilohertz. Okay. Okay, so basically what I want to do now is plot these points, basically do a graph using the points the data that we got over here from the experiment. So what you need to do is do a graph, and as we talked before in the previous video, we need to use a logarithmic scale here. So okay, so basically in order to do a logarithmic scale, you do need to consider, you do need to basically first of all decide whether you want to do your graph in a landscape mode or in a basically the other way around. There is landscape and portrait way, so it's either portrait or landscape. So I don't really know if these basically fit over here. My voltage goes all the way up to, so you see over here my output voltage goes from 1.9, 0.5 all the way to 28 volts. So 28 divided by 2 is 14, and I think the output voltage is going to fit on the vertically here, and then we can plot the frequency down here. So what I'm going to do is that I'm going to take this time as, of course, normally you're supposed to use a pencil, but if I use the pencil you would not be able actually to see it on the camera, so I'm not going to use the pencil, and then what I'm going to do is leave some space over here. Probably this would be okay. So then you can do it this way, and this is basically 0 volts down here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that way you can do it. So that's basically 2 units. 4, 6, 8, 10, 12, 14, 16, 18, 20, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, 26, 28. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Something is wrong. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, that's 26. And that's 28. Okay, so that's 28 volts. And then what you see, we have a problem down here, and my input voltage is actually changing because of the problems that my function generators has. but that's not going to change much about I mean, it's not that important really. I'm going to assume that the voltage has not changed all throughout all of these data points, okay? And I'm just going to assume that these are the actual right values. So I'm going to plot these points against the different frequencies, and to get to basically, if basically I'll start with 10 Hertz over here, I'm going to start with 10 Hertz over here, and then basically I want to go all the way up to 10.1 megahertz. Okay, so 10.1 megahertz, that means that let me see, you need to basically to count how many units you have down here. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see how the lengthwise what that is. So 5 of these is 10 units. 1, 2, so that each of these is basically 0.5 units, so or 0.5 centimeters or 5 millimeters. So if you come all the way out down to here, so you have 25 units all the way up to here. So this is 25, okay? And if I want to basically, I would need to go from, for example, 10, I would need to go from 10 Hertz, and then times 10 is equal to 100, times 10 is equal to 1,000, times 10 is equal to 10,000, and times 10, this is 10k, this is 100k, this is 1 meg, so this is 100k, 100k, 1000k, which is 1 megahertz, and this is 10 megahertz. Okay, and I think 10 megahertz, and then we need to go all the way up to 100 megahertz. So I need basically 1, 2, 3, 4, 5, 6, 7 units over here, and 7 units. So if you have 25 of those small units, if you were to divide them between these 7 units, 1, 2, 3, 4, 5, 6, and 7. So each of them, if we give each of them three of those units, then that would be, I suppose, things would work out that way. So oh no, I'm sorry, 6 basically. 6. So that would be 1, 2, 3, 4, 5, 6, and 7, something like that. So that would be 1, 2, 3, 4, 5, 6, and 7. Okay. So, and that would be now, for example, 100 Hertz. This would be 100 Hertz. This would be 1,000 Hertz. This would be a 10,000 or 10k Hertz. This would be 100k Hertz. this would be at 1 megahertz, this would be 10 megahertz, and this would be 100 megahertz. Okay, so this is frequency in hertz, and this is V of out in voltage peak to peak. Okay, and this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so now when it comes to your data, you don't of course need all of these points. A few of them is enough, are enough. So for example, at 10 hertz, your V of out was 28 volts. So this is 1 point over here. For example, at 100 hertz, we were at 29 volts peak to peak. So this is 26, 28, 30. At 100 hertz, we were at 29. At 1 kilohertz, we were at 29. And of course, you see this I mean, the fact that the voltage over here is 28 volts peak to peak and 29, it's something related to the function generator. Otherwise, the voltage would actually begin at 29 volts and then starts to fall down somewhere over here, but it's related to the function generator, nothing related to this experiment. At 10K, for example, we are at 24 volts, so 24 volts over here. At 100K, you are at 5 volts. At 100K, you are at 5 volts. Now I could actually pick a couple of points and do the graph very quickly, but if I want to show you how you can actually plot these points midway, between the for example 1000 and 10K and 100K and so on and so forth, what we can do is that, for example, at 10 kilohertz, we were at 24 volts over here. Now at 24.8 kilohertz, right? At 24.8 kilohertz, we were at 15 volts peak to peak. Okay, so basically you are here at 10 kilohertz and you want to get to 24.8 kilohertz. You are at 10 kilohertz and you want to get to 24.8 kilohertz on this scale over here. So basically you basically need to multiply by some number, or some you need to take your 10 and multiply it by some power of 10 in order to get to 24.8. And you do this because it's a logarithmic scale. We talked about that in the previous video. So 10 raised to power x is equal to 24.8 divided by 10, which is equal to 2.48. So 10 raised to power x is equal to 2.48. So x is equal to log, for example, base 10 of 2.48. And log base 10 of 2.48. log base 10 of 2.48 is equal to 0.39, 0.4. Okay, so 0.4, that means that the distance between 10K and 100K, you have to basically you have to move forward by 0.4 units. So this is 1, 2, 3, 4, 5, 6. So this is halfway between them, halfway between 10K and 100K. And if I somehow so 0.4 would be 1, 2, 3, and 4. So that would this point over here would be basically that frequency, 24.8 kilohertz. 24.8 kilohertz, and that corresponds to, for example, 15 volts. That corresponds to 15 volts over here, 15 volts over here. Okay, so that's basically somehow one way that you can do this. Or at 43.6 you're at 10. At 43.6 you're at 10, meaning that so when we say that at 43.6 you're at 10 volts. So since you're starting at 10, you take your 43.6 and divide it by 10. So that's 43.6 divided by 10, and you take the log of that, and it's going to be 0.6 units. So this is 0.5, so this is 0.6, and at that output you are at 10 volts. So 10 volts would be right over here. So this is basically this point over here is it's actually 43.6. Okay, and so that's basically how you find your way through your logarithmic scale. And then at 102 kilohertz you're at 5 volts. So this is 100 kilohertz and this is 1 megahertz, right? So at 102 kilohertz you want to find 102 kilohertz. So you start from 100 kilohertz and you basically want to go to 102 kilohertz, right? So the way that you can do it, you can find the log of basically 102, log of 102 divided by 100, which is equal to 1.02 divided by 100, because you start at 100, and then you will have 8.6 into 10 raised to the power 8.6 related. Because when I calculate this, I might have actually made a mistake. So you start at 100, and you have to multiply by some power of x by some power of 10 to get to 102, right? So then 10 raised to the power x is equal to 102 divided by 100, which is equal to, so 10 raised to the power x is equal to 1.02, and x is equal to log base 10 of 1.02. log base 10 of 1.02. So log of 1.02 is equal to it doesn't make any sense. It's giving okay. So that's actually the same thing as, so 8.6 basically into 10 raised to power negative 3. 8.6 into 10 raised to power negative 3 is the same thing as 0.0086. That's 8,000th of a unit. It's 8,000th of a unit. That means that you're just very close to, very close to 100. So I just take it as 100, and because it's practically 100 anyway, and then the output here is 5 basically. So somewhere over here, and then at 216.6, at 216.6, so log of 216.6 0.33. So this is basically 216K. 216K. You're at 2 volts. You are at 2 volts over here. You are at 2 volts over here. And at 415.2. At 415.2. So this is 100. This is 10. At 415.2, so let me see, 415.2 would be log of 415.2 divided by 100. That's equal to 0.6. That's 1, 2, 3, 4. So that's right over here. And that's 2 volts. So this was supposed to be 5 volts, right? But at 102K, I'm sorry, 216, 2 volts. Okay. At 415.2, you're at 0.5 volts. Okay, so you're at 0.6. At 0.6 would be over here. So this is basically, this is 415.2K. You are at 0.5. So this is 1 and this is 0.5. So you are at this. This is your output. At 400 at 563K, so log of basically 563 divided by 100 is equal to 0.7. So 0.7 would be here, and your output is at 0.1. So this is 0.5. And 0.1 would be over here, and so this is 563K. this output here is 563K, and this is one of those points. Then you have at 930K. At 930K would be log of 930 divided by 100, which is equal to 0.96, around very close to somewhere over here, 0.96, somewhere over here would be 1.2 volts. So 1.2 volts would be somewhere over here, and then at where are we? So 1.6 megahertz, and now you have to start from 1 megahertz, and 1 megahertz is the same thing as basically 1 million hertz, right? So here we were working with you can take it as 1, right? You can take it as 1 and forget about the suffix and prefix and everything. So, or you can take it as a you can take it as 1 million. It depends on your opinion. But easier is that you take it as 1 and then multiply by the whatever you get from your calculator. So for example, at 1.6 megahertz would be meaning that you're starting at 1 and then you want to end up at 1.6, right? So that would be log of 1.6, and that means 0.2. So 0.2 would be 1, 2, 3, 4. 0.2, this would be 1.6 megahertz, and 1.6 megahertz you're 2.4 volts. So 2, this is 3, this would be 3 volts, 2.4 volts, this is 2.5, 2.4 volts. And actually the graph gets a little bit messy. There is no way to there is no way to write down all of your numbers, but well, there is no other way to do it. So 2.7 M would be, for example, over here would be log of 2.7. So you would get 0.4 somewhere over here, and the voltage is 5.4 volts. So 5.4 would be somewhere over here. At 3.9 megahertz you're at 10 volts. Log of 3.9 is 0.6, so 0.6 would be 1, 2, 3, and 4, and at that you're at 10 volts. So 10 volts would be right over here, and then you can still go to 4.7 megahertz, which is log of 4.7. We're at around 0.6, 0.7. So I take it as 0.7, and you're at 10 volts here. Sorry, 4.76. Log of 4.76 is 677, 0.7. You're at 11 volts. Okay. And then at 5.9 megahertz, you're at 7 volts, so 0.7.8 at 7 volts. That's 0.8, so 5, 6, 7, 8. Somewhere over here. So you're at 7 volts or so. 6 and 7 volts or so. And then at 5.9, 7.4 megahertz, 7.4, so log of 7.4 is equal to 86. Okay, so 5, 8, so somewhere over here you are at 3.8 volts, somewhere over here. Okay, at 9.4 megahertz, so log of 9.4 is equal to 0.97, so it's very near, very close to 10 megahertz. You're at 2.2 volts. At 2, this is 2 volts, so there, somewhere over here. And at 10 megahertz, you're at 2 volts. You're at 2 volts over here. Okay, so your graph is going to be, I take this point as the input, okay, and your graph is going to be something, like this. Okay, so that means that at this resonant frequency, 400, oh, it has to pass through this point as well. Actually, this is the main point. So at this resonant frequency, 563 kilohertz, you are at the lowest value of your voltage, somewhere around 0.1 volts, 100 millivolts, and then you see that your voltage starts this way, comes right falling down to the resonant frequency and starts rising again to this point to around 11 volts and starts falling over here. So that's basically how your circuit functions. Now, what I'm going to do now, I'm going to go read a little bit about this experiment, see if there is anything important that we missed here, and I'll be back with you with the rest of this experiment. Okay, so that was it basically for this filter, which was basically called a notch filter. It's also called a band reject filter, if I'm not wrong. Okay, so that was basically it for this experiment. I'll see you in the next video.